So, good evening everyone. A couple of years ago on the Dev Club, one of the events, there was already a presentation about Starship which was dedicated to proving actually the fact that delivery based on robots or robotic delivery or delivery with the help of robots, autonomous or semi-autonomous, is possible. Well, yes, it is possible, but well, we have proven that it is possible, but we want to be massive. We want this delivery to be scaled sky high. We want to conquer the world, actually. And a couple of years ago, the number of robots that the system was able to maintain was around 20. And now we have solved the scalability problem. And I will briefly also talk about history and what led to our decisions and how we did it. So, what is the Starship? Okay, I can probably skip that part because Ahti told you already. So, the last mile problem. The last mile problem is quite essential. It's expensive. And that's the main problem. It's expensive because if you rely on human delivery, you need to order a courier. So it involves a human, it involves a vehicle, it involves whatever planning on the delivery company that might not be suitable for you. So a lot of obstacles that hinder and affect your experience. And we want it to be affordable and like on demand. This is what the people want. So the mission is to build local on-demand delivery service, and local is within 2, maybe 3 kilometers radius. And this is where we do it, right here. So this is our business model. Quite obvious. So we are focusing on delivering food, groceries and packages, and the maximum weight that we allow in our robots is 10 kilograms. So that's an average shop basket that you purchase in a grocery shop when you go there in the evening. But with the Starship robots you don't have to go to the shop. You can order and basically your package will be delivered. Starship robots, they drive on the sidewalks with pedestrian speed, so not more than 6 kilometers per hour. They are equipped actually by different sensors, cameras, ultrasonics. They can be supervised by a human operator at any moment. Usually they are not, because we want to achieve as high autonomy level as possible. But if in case the help is needed, the operator is always there to catch. So what we have? We have sensors, for example cameras, and based on these sensors we use computer vision technologies to detect obstacles, moving parts like cars, bicycles, people, other robots. So we use 6 wheels, and this gives us a possibility to go over the curbstones, which are 20 centimeters of height, which is pretty nice. We can cross any sidewalk in the city. Now, what we want? We want it to be 99% at least autonomous. We want the operator to make fast decisions, so the information provided to operator must be concise and clear. For operators this means fast context switch. For us, the backend side, it means a lot of data coming from a lot of sensors. And another thing is that the fleet of robots is geographically distributed. So for example, we have a fleet in Tallinn, we have it in Hamburg, in Milton Keynes in England, in Washington DC, in Bay Area, California, and now starting in Arizona. So it's a worldwide fleet. And actually we can have it anywhere. And all the commands coming from the robot into the robot must pass the database for consistency, so that we are able to analyze and replay situations. Now, let's go to the data transfer. So, the first and essential is video. So, anybody can plug a webcam and control it, put it on a quadrocopter, whatever. And how can that be hard? Well, this is where the hard part comes into play. Different robots in different regions of the world, controlled by operators that are also located in different regions of the world. And we have oceans with the latency that we cannot overcome, because unfortunately nothing yet can travel faster than the speed of light. So we have to cope with that. Now, what do we want? We want the command flow from robot to operator, or from operator to robot, be less than a quarter of a second. Why is that? Well, if a robot travels with 6 kilometers per hour, which makes it almost 1.4 meters per second, then 1 second is 1.4 meters. So if a command takes 1 second to reach the robot, then the robot has already driven almost 1.5 meters. That means if the command is critical, like stop at the crossing, well, the robot is most probably hit by the car by that time. So this is why we have such a strict constraint, quarter of a second. At this time, the robot will not be hit by a car and will be able to stop and automatically jump back if it's required. So let's briefly glance on the history.
Really jumping or just...
Well, it's called jumping. It like drives slowly and then it can do like that and stops. And that jump back is 0.5 meter maximum distance. So it's a safety feature built in the robot to avoid...
Still with the wheels, you mean just
yes,
going back?
yes,
Just
yes.
going back.
It's a speed back.
It's not jump back.
Different people
well.
are behind bad things. What's that?
Yes.
Bad people happens, bad things happen to the people. Well, it's the same if you are walking behind the person and the person accidentally stops and moves back, you collide. Well,
how does that comply with Asimov's first regulation?
Actually, if you make a car accident and there is kids with parents inside car, then it's better to back and hit just one person.
yeah.
Thank you.
So, the history. Before we had one camera, WebSocket transport, quite slow. Then we changed the streamer coding. Well, it has become a bit faster, but still slow. We added more cameras, even slower. So, I mean, slower in the sense that how fast the video frames reached an operator. All right, we changed then the codec to a custom H264 encoder, which gave us some improvements. And final step, implemented by one of our teams, was complete change of a transport for video using custom-made UDP protocol based on the ideas of some serious research of reliable transport or semi-reliable transport over UDP, where you can assign priorities to packets, and the higher priority is, the more reliable that packet will be, including 100% reliable. But that travels.
Custom means like it's fully done by you.
It's
Or
fully,
codec
a codec as well, fully not by me personally, but by the other team, but by STARSHIP. It's fully custom. but it's using some white papers of reliable UDP transport research. And that actually gave us the desired time for video transfer, so that the operators can actually see immediately, or well, quite fast, what is happening with the robot and react. Now, but what about everything else? So, what we have? We have to the operator, because operator works behind the browser, we have a WebSocket connection. Persistent WebSocket TLS connection. Then we are measuring constantly actually the round trip time of all the commands going through the server from robot to operator and back. We make certain decisions what commands can be dropped if there is a quite high number of the commands going through. We even made pretty simple custom made load balancer, which actually allows us to do smart balancing based on persistent connections and the load that goes over each connection. So we are distributing the load this way quite evenly between our services, connectivity services. So, control panel. Well, control panel actually sees 5 cameras. So if you open the panel to see what the robot is doing, to look at the world by the robot's eyes, you will see 5 cameras and information coming from 5 cameras. Every camera by default works on a 4 FPS ratio, which can be increased up to 8. But that means that we immediately have up to from 20 to 40 FPS in browser for all 5 cameras. And every FPS frame, it's data. Might be quite a lot of data. Also, in the panel we have live telemetry data from ultrasonics, from other sensors, because we are testing different robots with different types of sensors. That's why they are not completely the same, and different information may be displayed at the operator panel. And we are targeting at the at maximum half a second cycle for cry for help situation, that if a robot is in danger, then operator can react, and the time between robot saying that he is in danger and getting the command back from operator what to do should be at maximum half a second. And we are currently achieving that, even across the ocean. So, this is how the panel looks like, actually. The first top part is a panoramic camera. It's stitched from 3 cameras, so it's actually like 3 cameras data. You can see the stitching parts. The stitching is done on the robot directly, so the robot transmits this long frame, and here are 2 backside cameras. So the robot automatically can detect the traffic lights. It knows that here is the crossing, so we can see the power of a 4G signal. How much battery does the robot have? Then we can see that it helps itself with the light. There are some other commands possible. We also can see the map, the route, and here it says that it's driving in autonomous mode, so without the operator help. And here are ultrasonic and what's the blue? I don't know, something new was installed, but these pink are ultrasonic. And it actually says operator needed. So it waited on the crossing for quite a long time and created the task for operator. It requests operator help, because we cannot allow ourselves to let robot wait as much time as it can until it can do the crossing, because the battery may run out and we have a promise of delivery. We have a time to fulfill. Now, the robots actually produce quite a lot of data. It's around 2 gigs of structured data, telemetry data, whatever, and around 100 gigs of unstructured data, which mainly comes from images and video.
So
yes.
2 gigs a day each robot?
Yeah.
Okay.
And we will come to the total numbers later. So we are transforming some part of it to the data warehouse for analysis, and we can actually execute some queries against unstructured data with the help of SpecTex, and we are rerunning algorithms that verify how our neural network detectors work on a daily basis, and in fact several times per day. And if these algorithms are adapted based on the data, well, we are on the good side, and they are adapting that on a weekly basis, because new and new data come in every day. Like recently, maybe half a year ago, they started to work on the nighttime driving. So these images were, they took images from the nighttime and applied them to the detectors, and saw that the success percentage went down, and they adapted, they retrained the network, adding these nighttime driving images, and it's back again to the good level. Now, the sugar on top is that we have multi-connection set up. The robot doesn't operate via a single 4G provider. It can actually operate up to 3 providers, and in the United States and certain regions we do use 3 SIM cards in a single robot, and the robot actually decides based on online real-time analysis what kind of an operator is the best one to use now. Now, coming to the interesting part, maybe, the server side and the latency challenges that we have faced. So currently we have hundreds of robots, more than 200, almost 3. And there are plans to have this year to have 1,000. So robots are spread, as I said, across the world, which makes it a little bit difficult to cope with. And operators might be located anywhere. In fact, operators might even work from, I don't know, Hawaii. They only need to have an internet connection and VPN, then that's it. Now, the robots are transmitting from 5 to 7 data messages per second. This includes different messages about what robot encounters, telemetry, whatever textual information the robot can provide, or binary, well, small binary. And these messages are not that large, half of a kilobyte to kilobyte, but periodically robot sends a big message, 60 kilobytes. Then the robots are transmitting from 4 to 8 video frames per second, and each frame is 1.5 to 4 kilobytes. And the robot is, in average, operating for 10 hours, without break, actually. And single robot generates hundreds of thousands of data messages and same number of video messages per day. And if we have 100 of robots online, and we actually are having that, most probably now, and this results in tens of millions of messages from robots coming to operator through a server. So we need to deal with that amount somehow. We need to store the data somehow. We need to deal with the possible latencies, with the scalability, because we want it to be scaled. We want this service to run 24/7. And it is actually running 24/7 since we launched this week Northern Arizona University. Currently we have operations in different parts of the world that last in total 24 hours. This scalability service that serves the robots must be resilient, and it must scale on demand, because when operations start either here or in the United States or in Milton Keynes in England, we need the number of robots increase rapidly. It can jump from 50 to 90 like in 1 minute, and number of operators also increase because they come to work to serve the robots, to help them if there's a need be for that. So this is a scalability, and it's only starting, because with the time when we will launch more and more sites, these scalability demands will be more and more. They will grow. And of course, self-latency of this service must not be huge. Otherwise, it doesn't make sense to have a connectivity service that adds a huge latency due to this car heat problem that I described a bit earlier. And there is a problem that we cannot overcome ocean latency. But how we can solve it? We actually solved that. We extracted this connectivity service as a standalone service. Let's call it a microservice. We can scale that one part quite easily. We can have the connectivity service, the service that serves connection between robot and, let's call it, a central server, and operator and the central server, and in the end the robot. This service is standalone, and it can be scaled, well, as much as we can allow ourselves, or as much as Amazon can allow us to scale. We use service discovery to execute this on-demand scaling. So once we need more instances,
Okay.
Just continue.
if we need more instances, we just launch more instances. How hard can that be? Due to smart load balancing, these instances will end up having evenly distributed load.
You're talking about
Yeah.
scaling the application layer.
Yes,
right?
yes.
But all these messages are being written to the data store, right?
This writing to the data store is asynchronous. It doesn't affect the complete flow.
So it first arrives to the operator screen, and then it travels to the data
Well, in parallel.
in parallel. So basically, operator is not dependent on the data persistence
No.
being okay.
No.
Got it, yeah.
And this way the data persistence can be scaled independently if we have a need. And actually we, so the internal messaging, so since there are standalone services, internal messaging is done by using Nano MSG library, which essentially is a core of ActiveMQ or RabbitMQ. So actually it's the same developer, the same author that wrote the core of those message queues, decided to improve it and have published quite many years ago this libnano message, which is actually used by us. So we wrote a small wrapper around it to provide it in a suitable way, like more convenient way, and it's embeddable into our applications. There is a drawback, of course, that the messages sometimes can be lost because internet might be fragmented, the services might go down, whatever may happen, but, well, there are a lot of messages, and important messages are always republished, they are always acknowledged. So commands, for example, like stop command, it's always acknowledged, and if it's not, it's republished, and it's like pretty fast. We also designed the layout of our services to be so that the number of travels across the ocean is minimized to 1, if there is a need for that. So if there is a robot in the United States and operator is sitting in the Europe, then the command from robot to operator travels only once. Unfortunately, this was not the fact 2 years ago. This was one of the reasons why the solution that was existing 2 years ago was not able to handle many online robots.
A question.
Yes.
Why do you necessarily have to have this problem? Isn't that cheaper to just establish different operator offices in different continents?
Of course it is, and we have different operator offices, but for example, when we launch a new site, we cannot hire 5 new operators in 1 hour.
But do you launch a new site in 1 hour?
Each hour?
No, but it's
also about the utilization of operators. For example, you don't want operators to be idling. Imagine the operator in Tallinn idling, but there are tasks in the US to be solved,
Yeah.
so they are routed there. So
Okay.
it's kind of utilization of the resources.
So it's basically only corner cases.
it's corner cases, but yeah, mostly currently, well, the problem you have sounded just now, it was a fact a year ago. Currently, most of the local, regional issues are solved by local operators. But still the solution exists, because if there is a need, then there must be a way to solve that. And we are still providing that. And yeah, as I said, and for example, we designed it also this way, that the robots connect to local services. United States robots don't connect to European services. That doesn't make sense. And the self-latency of this connectivity service is, well, it's around 1 millisecond and even less. And the communication delay introduced by nanomessage is up to 12 milliseconds. We recently executed the load test, launched almost 500 robot simulators, software simulators that actually produce the same amount of data that real robots produce and consume the commands that real robots consume. So from the point of view of a backend, it's like a real robot. It connects to a service, it talks to a service, does whatever it needs. Now, back to real life. Currently we have 250 robots. And they have driven 250,000 kilometers already. We have been to 80 cities and have met 38 million of people. And we will grow. And the load test that we have executed recently showed that we can actually have up to 30,000 robots in a single AWS region, if we are talking about software. If we take a look at that, there are 4 AWS regions in the United States and 1 in Canada, we can say that, we can have up to 150,000 robots operating online at the same time in the United States. And the same for Europe, it's 5 regions. So the number is pretty high, and this connectivity service can actually handle that. Yes?
Why is there a constraint on a AWS region? Like, why?
Well, we are just using AWS. If we ever decide to use another cloud provider, we can have more.
Yes, but why? What limits the
Network.
amount of robots that can be served by
Network.
network?
We cannot utilize more network than it is given to us.
Okay.
Because all the messages, they actually consume a network, and network throughput is limited.
Okay.
So we actually will hit that limit. We will not hit a limit of latency, we will hit the limit of a network. And we cannot overcome that limit, unfortunately.
Another question is that every AWS region has the same network characteristics, or?
More or less, they can be negotiated, but you cannot. Well, if we become at some point in time such a big player that we will demand more, I think Mr. Bezos will give us more.
Like reloading the current network that providers provide.
Yes.
Is it because of the video stream, or?
It's both. So the data is like almost the same amount of information, the same amount of traffic if we count the data.
But if you disable video stream, if everything is okay,
It
will work autonomously.
And this is what we are trying to do. So it's a joke within the Starship server department. Does anybody hear how a tree falls into the wood if there is nobody in the tree? So if nobody observes the robot, a robot doesn't transmit the video. Currently we are trying to do that with the data, so that the robot doesn't transmit, well, quite essential part of telemetry to data if it's not observed, because it's not needed. It is saved on the robot side. At the end of the day, this data is synchronized to the data warehouse when the robot is sitting, idling in the hub, in the quiet, peaceful room, not on the street, in the harsh weather, like snowing, rain, whatever can be done. So we are targeting at solving this data, but with the current setup, we have a limit. Yes, when we optimize the data flow from the robot side to the server, this limit might be increased.
So basically, you don't trust robots yet.
I don't even trust you, sorry.
That's obvious, but I mean,
since robots use technologies created by humans, they also tend to make the mistakes that humans do.
Have you ever lost a robot?
No. We had a couple of times a situation when robot went offline, and actually, like, nobody knew where was the robot, but since we have a emergency recording at certain situations of the last minute of video that robot actually sees, well, we were able to discover the robot. And once there was one situation when people actually brought a robot to the Starship office in England because some accidental people saw that the robot is vandalized, and they helped the robot.
Did you detect any, hijacking attempts, like to control a robot?
Around 6 to 8 months ago, we ordered the penetration testing for robot, official service, which actually exposed some critical parts in the security, and we did everything we could to fix that.
But so far no one even tried,
Well, so far no one tried, or at least we don't know. When we ordered that service, the guys tried desperately, they did the best they can, and they did it. However, they were not able to go behind the robot. So the only thing they were able to hijack was the robot, not the server software.
You mean hijacking robot means we took the control of a robot or not?
They were able to log in as administrator, see all the commands. Spending time, you can deduce what every command means, and you can take control. So, people love our robots. And finally, we are hiring backend developers.
Just to add to that, Pavel mentioned several times that all the data goes to data warehouse.
Yes.
We have one data engineer.
Yes, this is our data warehouse representative. You can tell about amounts of data you deal with.
Well, you described it pretty well.
Yeah, but I have just shown the numbers per day.
Right. Yeah. All the robot data is queryable with SQL, several different versions of SQL, and we are keeping it in S3 in files. It's about 90 terabytes right now. All of it can be queried pretty quickly. But we're also hiring data. So
Yes.
come talk to me.
Yes.
Break.
Regarding data warehouse, I imagine you have a lot of videos, and
Nope.
that can be
Nope.
useful?
Nothing. Data warehouse is for engineering development and business side analysis and marketing and that kind of stuff. We have 0 bytes of PII data, including videos, pictures, names, emails.
I can talk about video.
We don't have any of that.
We store, but as you have seen from the panel example, 30% of the video from the top is obfuscated because of legal reasons. We are not allowed to record faces of people actually. But we store some videos from robots. They are stored in the format of ROS bags. ROS is a robot operating system. They are also stored in S3, and they are used by computer vision department to actually execute their algorithms against these videos. But not all the videos are stored. They are cleaned up periodically.
I just thought that it would be useful for police to ask from you.
Well, if there is a case of vandalism, and we have a video with the recording of a person who actually attempted or did damage to the robot, we can provide to the police this video as a fact material.
But if it's a car accident, for example, somewhere, or let's say some
And
illegal
for car accidents as well. So there was, last summer, there was a noticeable car, let's call it an accident, in here, in Tallinn, when one of the cars actually hit the robot. The robot was crossing the street on the crossing, official crossing, and the car was turning right, and it hit a robot a bit, and the video has proven that the car was not blinking, so it was not showing the turn signal, which from the human perspective is a violation of a rule, but, well, it's a robot, who cares?
the big picture, like, taking control over order on the streets, because you can record in real time what the, bad activity between even humans.
Well, this is not a part of our business, and it's not requested by anybody.
But yet,
But if this will be requested from police,
I will have to interrupt you guys for a second. We're really running late on our schedule, so let's continue with
Yeah.
questions.
You may ask questions
after
later.
the talk in private, and we have 5-minute break, and then we crack on with the second talk. Thank you.
Thank you.
Break up.